In our academic career, most of us will already have heard about Brownian motion quite a lot. It is a random movement of particles. We can extend this process to surfaces and use it to create so-called Brownian surfaces. The probable height differences between points on a surface such as this will be larger the further away they are from each other. This is modeled using Brownian motion. Since the self-similarity found in nature is apparent in fractal Brownian surfaces, these are used to model real-life terrains. But because of this lifelike feeling created by these surfaces, it is also a very common way to generate terrains in games, for example. Today we will look further into the algorithm that goes behind this and how we can use it to validate certain mathematical functions. To understand how these surfaces are made, let's look at how they are created. Brownian surfaces arise from a non-stationary Gaussian process. Non-stationary means its statistical properties, like mean or variance, change depending on position or time. The process develops according to its related covariance function seen here. It describes how many points are connected. The H parameter, also called the hurst parameter, describes the roughness or randomness of the surface. Now let's see how this is implemented in practice. We use a fast Fourier transform, or FFT, filtering algorithm, one of many possible algorithms. The algorithm begins with white noise where all frequencies are equally represented. Then, a discrete Fourier transform is applied, transforming the noise into the frequency domain. Next, a filter function, which depends on h, is applied. It scales down higher frequencies for larger h values. At last, an inverse FFT brings the data back to real space, and we have our Brownian surface. With the underlying process understood, we can now explore how the hurst parameter affects the landscapes. As the hurst parameter grows, the long-term dependence of the surface increases. In other words, the surface gets smoother because the different points are more dependent of each other. When constructing a Brownian surface with a hurst parameter smaller than a half, you will find a naturally looking surface, just like a mountain range. When you overlay a water level on this mountain terrain, islands and bodies of water will be created. This water, by the way, can also be seen as a fractional Brownian surface itself, although it has a lot less variance in its height. As also explained in the lectures, dimensions can also have non-integer values, a fractal dimension. This is also the case for the surfaces built by Brownian motion. The fractal dimension can be calculated by subtracting the hurst parameter from 2. To validate this formula, we computed Brownian surfaces with different hurst parameters. We then overlaid this surface with a grid of boxes and counted how many boxes were hit by the surface. We did this with different sizes of boxes to calculate the fractal dimension in a different way. The logarithm of the amount of touch boxes should be linearly dependent with the logarithm of the scaling factor, that is, the size of the boxes, for which the slope should be equal to the fractal dimension. This way, we could calculate the fractal dimension using this box counting approach, and confirm with this the relationship between the fractal dimension and the hurst parameter. In our results, the slopes were not always very similar to the actual fractal dimensions. We will discuss this further in our report, but for this video it is out of the scope. The book The Science of Fractal Images by Barnsley, Devaney, Mandelbrot Peachin, Soap and Vos, outlines a background to Brownian surfaces and explains the algorithms used to create them. Below is a picture of the book where mountains are simulated as Brownian surfaces. The 1986 Taylor article, named The Measure Theory of Random Fractals, was heavily used in the making of this project. The article explains how general Brownian motion is generated, in our case a surface, and it also shows the fractal dimension of Brownian surfaces to be equivalent to 2 minus the hurst parameter. The video "Fractals are typically not self-similar" by 3 blue, 1 brown was used to get a deeper understanding of fractal dimensions, and was used extensively for the formula with which we empirically calculated the fractal dimensions of our surfaces.
This video about Brownian surfaces was made by Nils and Mees. We hope you enjoyed watching.